Hello, today we are going to talk about other measures of disease occurrence. The other measures of interest in veterinary epidemiology could be divided between mortality and morbidity, which basically in terms of mathematics they are the same with incidence and prevalence, but it depends just what it's our interest. It's measuring the deaths or it's measuring the cases of disease. So hence the mortality, which deals with all fatal cases, and the morbidity, which deal with all sick cases. Other specific measures are like vital statistics, which measures the proportion of newborns or the production levels, or other indicators or categories which could stratify the disease or the deaths by specific groups, let's say by age, by gender, by husbandry level, or even by geographical areas. We start with cumulative mortality, which is basically the cumulative incidence in terms of calculation, and it can be calculated as a number of individuals that died during a particular time above the number of individuals in that population at the beginning of the period of the study. And to illustrate a bit more, we would go and follow through a flock of 10 sheep through 12 months, and we'll measure the mortality caused by contagious agalactia and also other factors as well. So if we follow through the animals, we would see that the number of deaths due to the disease are 3 deaths for the period of 12 months. Therefore, the cumulative mortality in this case is 3 animals out of 10, which makes 0.3, or let's say the cumulative mortality for this population was 30%. The mortality rate, it's another measure which is more likely like incidence rate rather than the cumulative incidence, so it has a time component as well. So the number of deaths the numerator basically is the number of deaths due to a disease that occur in a population during a particular period of time above the sum of the total time of all animals which have been at risk of dying into that population. So it's the timing here, it's important because we in the denominator we include the time at risk of dying of all animals in the population. In our example, we have two methods like we used also for incidence rate, and there is the exact method and the approximate method. In the exact method, we measure all different small bits of time for each animal. And based on the exact method, we would have 80 animal months, which is the total contribution of time at risk of dying, in this case, for this 10 sheep for 12 months. And the mortality rate would be 3 above 80, which is the 80 time at risk, which would yield 0.037 animal months. On the other hand, we have the approximate method, which doesn't account on specific measurement for each animal, but it's averaging kind of a concept. So in order to calculate the approximate method, we have to estimate the average number at risk over the period by adding the number at risk in the beginning and at the end of the period, and then divide this by 2, which means the average population. And if we look at the example, we would say that we start the study with 9 animals because one of the animals was brought into the flock later on, so it was bought, and therefore we have 9 in the beginning and 4 at the end. So we would have 9 plus 4 divided by 2, which would give an average 6.5. And then we would have the approximate method calculation for mortality rate would be 3 animals on top of 6.5 population times 12 multiplied by 12, which would yield 0.038 per animal month, which is pretty near to what the exact method calculated. The proportionate mortality, it's another indicator, but it's used in the denominator that all of the deaths, and not the size of the population in which the death occurred. So that's total deaths would be the denominator, while in the numerator, so on top of this, would be the death specific to a certain cause. So each of the death causes would count in the numerator, but in the denominator would be all total deaths. And if we sum up all the percentages for each of the specific death causes, we would end up having 100%. If we take the example, we would see that we have in total 5 deaths over 12 months for the 10 sheep population. And we have to split those deaths by category, and we say that 3 deaths have been caused specifically by the disease. 1 death was caused by the shepherd, so relating to the joke in the beginning, so the shepherd eats the sheep, so 1 is from the shepherd, but also the wolf damaged the population, so we have also 1 death by the wolf. And therefore, the proportionate mortality for this population would be 3/5, which is 3 from the disease and 5 is the total death count. We would have 60% mortality due to disease, and then we would have 20% mortality for each of the shepherd and the wildlife. That's how we calculate it. And if we sum up 60% from the disease, 20% by the farmer, and 20% by the wolf, we would have 100%. So that's how we calculate proportionate mortality. The case fatality, it's another indicator used, which, as the name says, is the number of animals which died from the disease out of all animals which was sick. So basically not all sick animals die, so the case fatality counts only those animals which died from the disease, and the calculation is number of cause specific deaths, so from that specific death among the incidence cases, so among the infected animals, the diseased animals, over the total number of incidence cases, which is over the total number of diseased animals. And it's a measure of severity of illness, and it's used to estimate how grave is the situation with the disease. Taking the example, we would say that in total number of diseased animals have been 4 during the study period, because we have animal G which did not die from the disease. It was sick during the study period, but it didn't die. We count 4 sick cases, but we have 3 deaths, and therefore the case fatality in this scenario is that 3/4 would make 75% of case fatality. Or if we simplify this fraction by the numerator, we would have 1 death per 1.3 new cases. Morbidity measures are same like the mortality measures, so the calculations are done exactly the same. But in this case, the focus is mainly on diseased animals rather than dead animals. But what's important here is that mainly the incidence and prevalence concept are used toward diseased animals rather than with dead animals. Therefore, we had many measures named by mortality during this lecture, but there is no error even if you say incidence of mortality or incidence of disease, so that's fine. But in terms of outbreak investigation, when the morbidity measures are done for a very short, are calculated for a very short period of time, especially during an epidemic or, like we said, during an outbreak investigation, the term of the risk, which is, let's say, the cumulative incidence of a disease, of diseased cases, is called attack rate. And then attack rate could be different attack rates. It could be an overall attack rate, so for all the population, but it could be also secondary attack rate, which is the cumulative incidence among contacts. So we have the primary cases which infected other cases, and the cumulative incidence in this group of contacts which develop the disease after being in contact with the primary cases is called secondary attack rate. And the secondary attack rate is calculated as number of cases among contacts of primary cases over the total number of contacts. Another measure especially useful for outbreak investigations is called the food-specific attack rate, which leads when we do investigation of poisoning or other alimentary diseases in animals. It's calculated as number of animals who ate a specific food and became ill, and therefore we divide that by the total number of animals which ate that specific food, and then we find food-specific attack rates. So we stratify by different food sources the population. In order to illustrate the overall and secondary attack rates, we take an example of infectious bovine rhinotracheitis, IBR, which is an infectious disease of cattle and can be spread through direct contact and through fomites, so mechanical vectors, and also in aerosol mode, but the animals should be within 5 meters to each other to infect each other, so we can consider basically as a direct contact, so there will be animals which are in very close range of 5 meters to get infected from this disease. And let's suppose we have a naive population in a village and we have an outbreak of IBR. And the village has in total 1,000 cattle. And in the village initially there have been 18 cases in different farms. So we have 18 cases in 18 different farms. And the subpopulation of these 18 affected farms, it's 86 cattle. And if we follow during our outbreak investigation, we would have that after one incubation period, we would find out that we have 17 animals infected in those 18 farms where we had the initial 18 first cases. And those are considered, the initial first cases, the 18 first cases, are considered primary cases. However, in terms of epidemiology, primary case is the source cases, but usually in animal science, when we do outbreak investigation, it's very hard to follow back or to trace backward to find the real primary case or the zero case. So we usually find the index cases, and those 18 animals are index cases, but for the purposes of this example, we call them primary cases because those infected other animals, so those are primary in respect to the secondary infections. And if we do the calculations, and we said that it's like the cumulative incidence calculation, we would have that 18 animals over 1,000, which is the overall attack rate, and for the whole population of the village, would be 1.8%. And then when we do the secondary attack rate, so within those specific farms which had the infected primary animals, we would have 17 animals, which was the secondary cases, above 86, which is the total population of the 18 affected farms, minus the 18 first cases, would give us 17 above 68, which is 17 cases above 68 of population at risk, which can be sick because 18 from those had already been sick. And then we would have 25% the secondary attack rate. And that's how we calculate the overall and the secondary attack rates. Other specific measures, as we mentioned in the beginning of the lecture, are related for stratification of incidence or prevalence by different categories. And therefore, these are more specific and can find causes or evidence the causes of disease. Like we said also for food-specific attack rate, we stratify by different foods, but there could be diseases that can be more affecting males than females. and so on, by different management system, let's say for avian influenza in a closed pen or open range and so on. So there are different stratifications by different categories, which would gives us hints to follow through, which can be a factor for the disease occurring. And in terms of calculation, they could be calculated in a similar way like the crude measures, but the numerator and denominator apply only to one or more categories of the population that we have selected to divide the population. A few more examples on very specific measures would be vital measures, which are the crude live birth rate and the general fertility rate. These are production-related measures, are not directly linked to the disease or to the mortality, but are still useful as measures. And for example, the crude live birth rate, it's a measure which is used to estimate the increasing of the population, and it's calculated as number of live births above the average population. While on the other hand, the general fertility rate is used as an index for the herd's reproductive performance, and it's the number of live births above average number of females of reproductive age. Again, the inverse, for example, of this would be that when we count mortality in the live births or stillbirths, let's say, for example, we study a Schmallenberg virus, we would count only the cases which died of the disease at the neonatal age or just born. So that's the inverse, let's say, of the crude live birth rate. Disease occurrence measures could vary a lot depending on the purpose and the setups on which they are employed and the different characteristics that we want to measure. Zoonosis incidence ratio, it's a measure which is used mainly to estimate the human health threat from a zoonotic disease and can be calculated as number of new cases of a zoonotic disease in an animal species in a given geographical area and especially at a stated period of time. And this is above the average human population in the same area for the same period of time multiplied by the time at risk. Here it's a distinction because in the numerator we use one species, which is the animal cases, and on the denominator we use the number of the human population. Another useful measure is area incidence ratio, which is a measure used as an index to estimate and to compare the disease in an area. And the calculation follows that the number of new cases of a disease in a given time period above the geographical unit area in which the observations are made. And that's basically how we calculate this measure. We will follow on the lecture series on measuring disease occurrence, so stay tuned and follow us in the next lecture. Till then, be safe and see you next time.